Okay, welcome. This session is on STAC. How many people know what STAC is? All right, a handful of people. That's great. So I'm going to be giving my name is Matt Hansen, work for Element 84. I'm going to be giving an overview of STAC and the software ecosystem that has been built to support it. And then we have several speakers that will be talking about their use of STAC. Okay, so STAC stands for Spatiotemporal Asset Catalog. And it's a specification for describing metadata for geospatial data, the geospatial data assets. The primary data source was satellite imagery really initially, but it supports a lot of different types of geospatial data. I think the big question that most people ask is why? You've probably seen the comic that shows all the standards, and the way to solve all of the standards problem is to create a new standard. Well, the thing is there really didn't seem to be a good standard for this. Like it wasn't just adding to the standard situation. It really was creating something new. The problem is that there's all these geospatial portals out there. Everybody has one, and every single one of them is different. The way that they work, the way that data is queried, and there's no standardization. So in order to get data from different sources, I'd need to go to all these different geospatial portals and do something a little bit differently. And when you look at the APIs, the situation is even worse, because one organization data provider might call it cloud cover in camel case. Another one might say cloud underscore cover. Cloud cover min. They all have slightly different variations on the same sorts of fields. Might be in integers, might be a floating point. So STAC was created as an effort to try and solve this problem. And it's really, I describe it as three different things. One is it's this defined set of metadata fields, defined metadata field names. So it's cloud underscore cover, for instance. It's sun azimuth angle. We have predefined names. So it's a common metadata model to describe different types of geospatial data. But the focus is on search and discovery. It's not a replacement for existing internal metadata. It's also a spec for describing how different sets of metadata within a data set are linked to each other. So a catalog links to collections, which links to items, and those items can be linked back to the catalog. And this is important because the data can be crawled and indexed. Because if your data cannot be crawled and indexed, then in this world, it might as well not exist, especially in the rise of all of the new big geospatial data that we're getting. If people can't find it, if it's just word of mouth or they have to copy and paste a link to get to it, then it's really not useful, especially for large automated pipelines. The last thing that it is, it's a dynamic API. So if you have your metadata that has been crawled and indexed into a backend somewhere, then now you can search it on arbitrary fields. And for this, we actually use the OGC feature API specification, which is just released to version 1, and that describes the actual RESTful interface with some extensions that are specific to STAC, such as the ability to search across multiple collections. So I mentioned what it is not. It's not a replacement for existing metadata, and this is a really important point, because we're not saying you should use STAC for your own metadata. Data providers have a lot of metadata that they use to keep track of things internally, and most of that data just isn't of interest to end users. They're not searching on it. They really want to just search on really usually a handful of items: cloud cover, nadir, viewing angle, depending on the data type. So we're not trying to replace anything. It's just an additional set of metadata that can be mapped from perhaps the internal metadata, perhaps set up as a proxy to an existing API. STAC started just a couple years ago. We just released a version 0.9 on Friday, and looking for version 1 in the first part of this year. There's been a wide variety of adoption. A lot of companies have been involved with this effort, both in contributing to the spec as well as using it for internal cataloging and helping out with software implementations. So the current state, I said, we just released 0.9. We're getting this fairly wide adoption. We are tying a version 1 rather than feeling like, oh, we've got a version 1 because we think that it's kind of the perfect final version. Instead, we've really had a focus on implementation. So in order to progress, we need implementations and we need data, because this has helped inform the spec. So even since the very beginning, version 0.1, let's build some implementations and see how this works in practice, and then we iterate. And this has been really the development model for the spec, and it's nice. I'm here contributing to the OGC coverage spec today, and the approach here is the same. It's really a focus on implementations, and this is a really great way to do things, because what seems great maybe on paper doesn't seem so great once you actually implement it. So the goal here is to have 1 billion records online when we release a version 1, and I think that there's some companies that already have millions of records that they're using internally for STAC. So it's being used quite a bit. When we release the version 1, we're also going to split the versioning of the API, since the API is really tied to the OGC API spec and could be more in flux. The core set of metadata is more or less pretty stable at this point. So the specification itself consists of 3 different entities. We have catalogs, and catalogs are really just containers for other things. It's a way to group and organize. And then we have collections. Collection is a catalog, but it has additional metadata describing the set of items that are grouped underneath that collection. And then finally, we have the items themselves, and this is the actual data. An item has assets, and these are the actual data files. Maybe they're not files, maybe it's some sort of API call, but it's the underlying data. In traditional EO parlance, a item would be a Landsat scene, and collection would be all of Landsat. The catalog fields here, pretty simple. Again, the focus is on simple simple metadata for search and discovery. So catalog really just has the main things is an ID, the title, the description, and those links are really important. Of course, we have STAC version and STAC extensions. You'll see these in all the different entities. Links are really important to the concept of STAC. We have the hierarchical links to link to catalogs and link to items so that it can be crawled, but we also encourage judicious use of links for linking to an about page or documentation or related software or data that has been that this has been derived from, so that you have a clear path of data provenance. STAC is really good for that purpose. Or you might have a DOI or a scientific paper. The hierarchical links that allow it to be crawled consist of these 5 different things, allow you to go up and down the tree. And when we look at the collection fields, we see all of the same fields that are in the catalog, along with a few others. We have things like license and providers. The extent is the spatial and temporal extent of all of the items within that collection, and then summaries, but it's really, as you can see, it's a summary of all of the items that fall under this. It doesn't have data by itself. There's no data specifically in a collection. And then when we look at the items, we've got the ID, type, and geometry, and bbox are, you might recognize as GeoJSON as GeoJSON fields, because STAC at its core is GeoJSON based, which allow responses from searching to be opened up easily into QGIS or into other geospatial software. I'm going to call out the properties here. I'll get to that in a second. Again, we have links. The assets are the actual data files. I'll get to that in a second. And a collection is just for identifying the collection that this item belongs to. There's no multiple collections. There's no multiple inheritance. An item belongs to a collection. So we really have two item properties in the core, which are date, time, and title. But then we also have several other common properties that have been split out because they're really optional and they're not appropriate in all cases. But a lot of data has well, I would argue that every data set has a start time and an end time. Oftentimes you won't use it for something like a full frame sensor that collects. You usually use the scene center time, but a lot of data will have start and end time. And then if it's been collected from some sort of platform, you have the platform, the instruments, and such. And so those are common optional fields. The assets, we have a rel type, which is, oh, sorry, no, we don't have a rel type. We have roles that sort of describe what the asset is used for, such as a thumbnail or a preview or a data file. And then href is actually pointing to the data itself. So this is just an animated GIF showing a catalog. Here we're at the top level catalog, and now we go down to the Landsat. So this is the Landsat 8 collection that you're seeing here. This is a little bit out of date. Some of the fields might have changed, but not much. We've got properties. There's a wide variety of properties. You might see some here that I didn't mention yet, because they're specific to EO data. And here we have the assets. Now this is at the collection level here. So you see there's no actual links there. What we've done at the collection level is define what assets are you're likely to find in any item that belongs to that collection. So the core fields in STAC are pretty simple, but of course that doesn't cover all cases. And so we have content extensions. I'm not going to get into any of those. I'll mention EO, but for the most part, this is a way for different types of data, SAR, EO, full motion video, whatever the data type might be, point clouds. We actually have a point cloud extension and a SAR extension, but there actually isn't a full motion video extension yet. But it's a way to add additional fields that just might not really be appropriate for all data providers. The EO extension, if you're familiar with STAC and have looked at it in the past, you might notice that there's a lot of fields that are no longer here. The EO extension used to have like a dozen fields. Now there's just 3. And the reason why is because the platform and the instrument and those other fields were also common to the SAR data model and other types of data. And so we moved those into these optional fields that are really common across all types of data. If it's been collected from a platform, you probably have those fields. So here we just have the ground sample distance, which is the commonly referred to as resolution, and cloud cover, and then bands is an object that allows you to tie assets back to spectral information, which is really useful. If anybody has worked with Landsat or Sentinel data, you know that you've had to go and find some web page that tells you what band numbers are which spectral bands, which is super obnoxious. You know, what's band 2, which is the red band. And so we have that spectral information in the EO band object, including the center wavelength and the approximate width and the common name. This is the most important thing right here, is the common name, because what we've done is described different common names for these spectral bands with an approximate band range. Now, these aren't exact, but if you have a satellite and you have a red band, it's going to approximately be in that wavelength. For The SWIR 1.6 and 2.2 bands, those have been named as such because if you have a sensor within that spectral region, they're going to be in those atmospheric windows of 1.6 or 2.2 microns, and so that's how those are named. So in the assets, over on the left, you see here's the band information. This is for Landsat, and then the assets. So if you look at B1 here, you'll see we have just indexed which spectral band that asset uses. And so if the file contains multiple spectral bands, you can put those in the order that they're in. So now a client can go through and find the assets that have the red band in it, or the red and near IR band for calculating BI, for instance. And this can all be automated, and you don't have to go and look this up online anymore. Okay, I'm going to quickly go through the software that has been created by a variety of people. So first off, if you have a spec, it's really useful to have a validator. This is the most boring thing to create, but luckily our friends at Spark Geo have put a lot of time into making an online linter and a Python validator, so you can go and validate your stack, and it will crawl the stack catalog and validate all of it. And so that's quite useful. The STAC browser, so I mentioned before, we have this static catalog. So you might not have your stack catalog in a dynamic API. It might be a set of linked JSON files. And so the STAC browser is simply, you can't search it, because this is just a bunch of files on S3, but does allow you to go through and browse through an entire catalog. So you can drill down, and in this case, it's showing that you can actually look at the previews, and these are cloud optimized geotiffs that are being dynamically tiled here. There's also a QGIS plugin. So this guy, Kevin Booth, had done this a couple sprints ago. This is pretty cool. It allows you to point QGIS to any STAC API, and then you can load the image files, and you can actually stream that, assuming that they're in a cloud optimized format like COGS. So that's pretty cool. STAC API is actually been renamed from something called SATA API, and right now it seems to be the only current up-to-date reference implementation of the STAC spec, and it has been around since the beginning, so it's been continually updated to meet each STAC version. It's a node library. You can easily deploy it to AWS. We're currently updating it for 0.9. I expect that work to be done in the next couple of weeks. And so the nice thing here is that it's all serverless with an Elasticsearch backend, and you can actually subscribe to an SNS topic and keep this thing up to date as new stack records are published, and I'll get to that more in a second. I'm going to skip by that because I am running out of time. There are a few other API implementations. Staccato is a Java-based library done by Boundless Geo, now Planet, and SAT API is a Postgres backend done by development team. Tom will be talking about PyGeo API, which does not have stack support yet, but knowing at the pace that he goes, it'll probably be done by the end of the week. Satstack is a lightweight Python library for creating stack catalogs. I won't go into any detail, but there's some useful tutorials in that repository. Some Jupyter notebooks that are actually a pretty good introduction to just sort of stack and catalogs and how they work. So those might be worth looking at. Satstack Landsat and Satstack Sentinel. I point these out only because they're pretty good examples of how to create stack records from existing metadata. And in the case of both, Sentinel's actually is up to date. The Landsat one's not. But both of them actually deploy a Lambda function. So this is actually a currently running Lambda function that will go and publish new stack records every time a new scene is available on AWS. So that's available for anyone to use. It's public. So if you want to know what the latest Sentinel data is from an hour ago, it's a pretty short latency, you'll definitely get data from today, but you can get that real-time data, and the message contains the entire stack record. So there's no need to go and look for anything. Pistack is a new Python-based library done by the folks at Azavia. Sat Search is a client for searching any STAC compliant API. And it's a Python library as well as a command line tool. I actually use this all the time. I find it one of the most useful things that I've actually done. Not to mention it has this really cool colored calendar in the terminal, which I'm pretty proud of. Somebody said it was a work of art, and I was like, oh, you know. So if you like terminal stuff, it's pretty cool. So this allows you to search and filter and sort of interactively get what dates this data is available for, and then you can go and you can actually download those files by specifying I want the red, green, blue data, and it will go and fetch those and download those files as is. Sat fetch is really quite similar. It just has some more geospatial capabilities into it. There's a Docker image so that it's easy to run. You don't have to worry about installing anything. Here we have footprints for Landsat 8 and Sentinel 2. And then I have Ngorongoro crater in the red polygon, showing that it's much smaller. And so here with Sat Search, I've searched for Landsat scenes. I found 18 scenes, and in 59 seconds here, I can go and download them because it's using the range requests. These are cogs, and it goes and fetches just that region for Ngorongoro crater, rather than having to get the 18 gigabytes of data that it would have been required to get all the bands and that you didn't want for the entire scene. The case is the same for Sentinel here, but I'm running out of time. SATA API Browser is a client that can be also pointed to any STAC API. This is under really early development, just was released a little while ago. So it's pretty bare bones, but the idea here is that it's an interface where you can just go to any STAC dynamic API and be able to search it. TakeStack is something that was created and used by the Pangeo community, if you're familiar with that. And this allows you to take search results from a STAC catalog and open that up as X-arrays, and then use Dask on the back end to do parallel high performance computing. So I think that's it. Thank you. Are there any questions? Tom. Tom's next, but is there any questions? There is, yeah.
Okay, so my question is for like searching over the ungridded data, like with the level 2, like the Landsat example. So what is the trick of actually doing the search so fast over these ungridded data sets where you're searching? Are you searching like over every single lat long pixel value and converging on the bounding box that the user specifies?
So
how is that? What is kind of the processing trick for that to be done?
Yeah, so we're not pixel, but for each scene. So each scene you have the polygon, not the bounding box. Because there might be no data regions there. So
how are those polygons created at the time of ingest, or how are those
yes. So in the case of Landsat, so it depends on the data if it's available or not. In the case of Landsat, that's generated from the metadata. Sentinel provides that as well. And then that's ingested into Elasticsearch, which creates the spatial index for being able to efficiently search it.
Okay, thank you.
Jeff up here.
Thank you. Is anybody using STAC for model outputs, like climate model outputs, which would have definitely a time component, possibly multiple elevations, multiple ensemble members?
So no, not yet. There's been a lot of chatter about an Earth systems model extension for STAC. There's something related called the Earth System Model Collection Spec, which looks a lot like STAC, but we can actually talk about that later, or you can talk to Rich about it. which is sitting next to you. Anything else? Okay, Tom. Tom's going to be talking about PyGeo API and the OGC API efforts in general.
Thanks, Matt. So I'm Tom Corlitis. I'm with the Meteorological Service of Canada, and I'll talk a little bit about the PyGeo API project, but I'll start with an overview of the current efforts and evolving efforts around the OGC API activities. So I'll start with a geospatial API revolution. I'm not sure how many people are aware of the efforts of OGC in this regard lately, but I'll go through a little bit of history, show my age at the same time. So from the OGC service perspective, I think in the 90s we started with things like SOAP, WSDL, and XML, service-oriented architectures, strong concept of relational databases as the back end, and the first OGC interface spec came out in 1999, which was OGC WMS. I think Jeff is here, who was one of the editors on one of those versions, so kudos. Fast forwarding to the 2000s, we had things like Web 2 and Ajax, as well as Slippy Maps, tiles, the whole Google Maps concept, and that turned everything on its end. In parallel to that, we had a lot of OGC standards come to the forefront around actual data. So featured data, coverage data, metadata or discovery, doing actual processes with data. So all those specifications sort of came around during this time as we evolved. Having said that, looking back, there are some. I think they were great for what they were at the time, but there were some realities that were evident with that version of OGC Web Services. So requests were pretty big as far as dealing with GML or geography markup language, and XML in general. Overloading HTTP. So we sort of abstracted away the HTTP protocol and made our own error handling inside of the OGC specifications. And if anybody has worked with OGC specs, they were traditionally very big and exhaustive and fully featured, which is great because it covers a lot of different use cases. But at the same time, it could be challenging. They've posed some challenges on creating simple implementations. So there's an example of what a WFS would have returned as part of a response. Other realities with regard to the architecture, they sort of ended up creating complex machinery and architectures for services to be crawlable or more internet or web friendly. Challenging for web developers to implement. So if I had a nickel for every time a web developer came up to me and said, how do I work with this standard, and where's the API specification, and pointing them to the OGC standard, which is very big and complicated, we needed to do better with that, and we've evolved in recent times. So as well as mainstream search. So mainstream search engines, Google or Yahoo or Microsoft or whoever, weren't as readily integrated with the OGC APIs and how to do discovery based on them. So we weren't as indexable on those search engines. So fast forward to, I guess, current times, we'll walk through some core concepts around what's going on today. So REST, which hopefully most of you are aware of, is basically using the HTTP specification at its core, actually using the HTTP verbs, status codes. This is sort of mainstream web and IT approach to doing APIs. JSON, I think most of you are aware of JSON, so it's a more compact form of passing data around, primarily on the internet. Very popular among web developers. It's also very closely tied to and implemented in programming languages such as Python or or JavaScript. So it's really easy to work with JSON and those programming languages, which are currently extremely popular. Open API. So Matt, you may have discussed this previously, but Open API is a industry-wide specification on how to describe a REST API. So it provides endpoints, request parameters. It's agnostic of programming language, so any programming language that you use can consume or produce Open API. This used to be called Swagger before it was more formally standardized. So there's an example of some of what we call an Open API document, which would describe an API and the sort of service metadata kind of thing here, but it also provides details on what all the endpoints are around the data and how you can interact with them and so on. And Swagger is really robust and cool Open API client tooling, which basically takes an Open API document and makes it really easy to interact with on the web. So suddenly, suddenly a web developer can open up a web page and click through all the different things that an API can do, see example requests, see example responses, and easily put together their own requests and response handlers for their own application as part of their application development. So basically a lot of the spec, a lot of a given API specification is actually rendered in Swagger, and it's a lot easier for a developer to look at a Swagger page as opposed to reading through a document. As far as OGC activity is concerned, in 2017, the W3C published a spatial data on the web best practice, which provided recommendations on formats and identifiers, access, licensing, and provenance. In general, being more webby with geospatial data. So that was a core canon of the current OGC API efforts, as well. Realizing we need some changes in how we work with it and how we develop APIs. So again, being more webby, being developer friendly, as I mentioned before, very lightweight specification development, removing HTTP as a tunnel, so removing using HTTP as a tunnel, so using HTTP without any overhead, and the idea of core and extensions. So Matt mentioned previously around the core stack spec, and there's a number of extensions going on there. So that same concept here. So that it's very easy to get up and running with a very minimal core, and you add complexity and functionality as you require it, as opposed to having being mandated to do it from the get-go by the specification. Timeline, so that W3C best practices paper, there was a white paper, an OGC API white paper in the same year. And around, I think, February or March of 2018, there began a series of hackathons or code sprints from OGC, which was nice to see. The first one was a WFS3, or now called OGC API Features hackathon. I think it was in Denver. Since then, there's been a Weather on the Web API hackathon about a year ago. There was also an OGC API hackathon in London on all the APIs. There was another one here a couple of months ago, and we're having one on coverages and processing yesterday and today downstairs. So these are really valuable exercises to get developers and specification implementers and editors, for that matter, to sit in the same room, test, find bugs, find areas for improvement, and iteratively improve the specification through testing and implementations. As far as the suite of evolving OGC API standards, so there's a list there of the 5 or 6 that are currently in scope, and in brackets I've put what they used to be called. So as you can see, with regards to features, coverages, processes, catalogs, they all have their counterpart from the OGC API efforts. So there is something called OGC API Common, which is the baseline for all of these. So any API should behave exactly the same for very common and core bits. And then they provide a lighter implementation on top, relevant to the actual to what they're actually trying to implement. So it's coverages or features or catalog discovery, what have you. Maps, obviously, and tiles. OGC activity on GitHub, I think it's valuable to mention that the entire OGC process with regards to evolving these standards has become a lot more open and available on GitHub. So there's activity and interaction on GitHub that's going on through the repositories. Most of them are open. So even if you're not an OGC member per se, you're welcome to interact. There's also many Gitter channels. So Gitter is a chat application which is sort of tied to GitHub. There's a lot of conversation going on there. So using those tools has proven to be very valuable. Standards are now written in Markdown or ASCII doc for that matter, and released as HTML. So trying to really lower the barrier and appeal to maybe the developers or non-expert crowd compared to before. Having said that, the activities in OGC are complementary with what's going on in STAC. So some of what STAC implements is actually the OGC API features with some extensions. So these are all being done in coordination. So there's very little sort of overlap. So they're being done with the mindset of trying to reuse whatever the other specification has done. And in the end, this will hopefully result in making it easier for web developers and any developers to create server or client software around these specifications. At this point, I'll provide an overview of an implementation that I'm working on, along with many others, to implement a lot of these OGC API standards in Python. It's called PyGeo API. So overview of the project, it's a geospatial data API framework. It's already compliant to the OGC API features specification as an early implementer. It's part of the open source geospatial foundation as a community project. And there's a very international team from Canada, Netherlands, Greece, a couple folks from New Zealand, and so on. So there's a lot of activity around it. I think some of the value propositions of the project are basically it's lightweight, extensible. It's in Python, which totally makes sense for geospatial and science. In terms of a technical overview, very light API and built on a robust plugin framework. So we're here for the sprint this week, and there's already a couple of developers downstairs developing plugins against Xarray and other NetCDF data. So the whole idea is that you don't have to do much data massaging, as opposed to using a plugin or using PyGeo API to connect your data easily, so that there's less of a data management effort on your part to publish data. Minimal dependencies, so it's really easy to install and deploy. There's an overview of how the whole thing is put together. There's a core, so you can essentially use PyGeo API on the command line if you really wanted to, or embed it into your own Python application if you're a Python developer. Again, we have a plugin framework which supports a lot of different backends for data integration. And we use a concept called data provider. So any backend that you have, the Elasticsearch or GeoJSON or CSVs. We also have a GDAL and OGR backend provider. So which means GDAL is a Swiss Army knife for data format translation. So we support that. So essentially, if your data can be read through GDAL, it can be published through the standards via PyGeo API. Quickly, some deployments at the MSC. We've deployed PyGeo API to provide our climate station data, the entire archive of all Canadian station data, as well as all of our hydrometric archive. So we're using PyGeo API to publish all of those. So tens of millions of records through this platform, and we're getting a lot of positive feedback from clients saying that it's very easy to implement and integrate this. There's a lot of R clients out there, JavaScript and Python clients, and most of this is due to again, lowering the barrier to access via the OGC API, the current OGC API standard development. So we owe a lot of thanks to the efforts in OGC because of that. So, but we are using it in production in the Canadian Weather Service, and we will be expanding our data offerings through there as things like coverages become available as a spec, and catalogs and so on. There's also an implementation of Glossus, a global soil information. So they have an implementation of PyGeo API, which is more focused on JSON LD. So you can see the link there. There's also another implementation out of New Zealand. So a lot of implementations of the software. Again, people find it very easy to work with the standard. I'll give you an example. I wrote a Python client probably 6 months ago, and I had a support for WFS1, WFS2, and now WFS3. And the WFS3 code was 60% less than either of WFS1 or 2. So really easy to write clients against this new paradigm. I'll probably stop there, just in the interest of time, but the presentation is online. There's a number of links there. Again, we are downstairs. Come visit us if you have any questions around the project. Thanks for your time.
Thank you, Tom. We're gonna, if you have any questions, you can search out Tom. We're just gonna move on, which is actually, I think, upstairs and then down the hall rather than downstairs. Christy. So Christy's going to talk about the USGS efforts in Landsat Collection 2 and STAC.
Hi, everybody. So I work out at Eros, which is in the middle of nowhere, South Dakota. It's really cold there right now, so I'm happy to be here. Unfortunately, we're going to get snow. I think I brought it with me. So we began transitioning Landsat data to the cloud starting in FY17 with our planning, and it's been a bit of a long road, but we're making considerable progress. And I just wanted to give a little bit of an update on that first. So these 3 bullets that you're seeing are something that we've held since the beginning of this project as our primary goals. Being able to get to a model of from downloads to direct access of the data is really key to my project in particular. Enabling data to be interacted with directly is really a huge step forward. I've been on this project, by the way. I was a project manager who made all the data free. So to me, this activity that we're doing right now is really one of the biggest things we've done since that point. And I think it's probably just as important as going down that road was then. The other thing, of course, is making sure that we ensure provenance and data stewardship along the way. As a data provider, that's really key to what our job is. Okay, so where are we today? Landsat data is actually now in AWS. We just haven't made it available yet, but we currently have over 8 petabytes of data sitting out in the AWS infrastructure. And right now we're working on all the hooks that we need to put in place to make it accessible. We did decide early on to go with a cloud optimized GeoTIFF, and we actually traded that against several other formats to include MRF and HDF and various other types, and chose to go with the cloud optimized GeoTIFF for several reasons. First and foremost is it's an easy transition from our current format, which is GeoTIFF. So, and it really met all the requirements we had with making the data accessible, with being able to provide a visualization interface on top of it. et cetera. So that's one of the key reasons why we went with COG. I did tell the team early on, whatever direction we choose is going to be a big decision, because Landsat tends to be a bit of a pathfinder with data sets. And so I think that when you choose a standard, it's probably something that's going to cause kind of a wave. So, and that seems to be a right decision, because a lot of other people are choosing COG as well. So STAC is another thing that came up a little bit later. And one of the reasons we decided to go down that path is because we are creating an interface where we want the data to be interacted with. And we needed something that gives users kind of an open source capability to really interact with that data and find the data. Landsat has 9 million images or scenes available at this point, and it's growing. And with our next collection processing, which I'll get into a little bit later, there's going to be multiple levels of those 9 million scenes. So it's a lot of data to sift through. You need to have an easy way to do that, and STAC provided that capability. I'm not going to go into all the nuances that Matt went into, but it really is something that I think is going to be a huge deal towards getting better access to the Landsat archive. Okay, so I talked about the new visualization prototype, and I'll show you a little bit of that in a moment, and also processing. So when we processed our data to collection 1, which meant that we processed the entire archive consistently at once, it took us over 10 months to do on premise. With the level 2 or the collection 2 processing, we're going to do that again with even more data, but not just to a level 1 processing, but also to level 2, which means surface reflectance and surface temperature. That takes even longer to process. So you can imagine how long that was going to take on-prem with similar hardware. Another major reason why we're moving to the cloud. So I'll talk a little bit about what is collection 2. So again, we're going to reprocess the entire collection. We're going to process it consistently with, the types of calibration that we apply, the types of the algorithms that we apply are all consistent. So that's, better for the scientists. What's different from collection 1? We're going to improve our geodetic accuracy with new ground control points. Those are going to be consistent with Sentinel-2. We've got improved metadata. So for example, our current products, we're starting to produce pixel level metadata. That's going to be even more improved with collection 2. We're also adding level 2 products, meaning we're adding surface reflectance and surface temperature, and they'll be processed consistently. So that's a big deal to a lot of users. This is just an example of what I mean by a surface reflectance product. And this is a pretty extreme example. On the left, you're seeing what a current level 1 product might look like. On the right, you're seeing that atmospheric disturbance removed from the product. And then this is just showing you what got removed from the product. And that would be in the pixel level metadata. This is what our current Landsat look tool looks like. It's not done yet, but one of the key features to this new tool is being able to get from the scene aspect down into the pixel aspect. So in this case, what I'm showing is an area that has clouds, and then I can turn on the flag to tell it to remove the clouds, and it goes out and finds clear pixels. It can only do that because we've provided the data necessary to know where the clouds are. Today, if you search on Landsat data, you're seeing cloud cover statistics that are based on the entire scene, but your area may be clear. So this is the kind of tool that can help you find just the clear pixels you need. One of the things we're also trying to do is to get to a point where users can interact with this data within the cloud versus having to download it. So what I foresee is being able to go in and search through your data, be able to create that data cube that you want, and then be able to just pull that directly into like a Jupyter notebook within the cloud, instead of having to download that data, and you're interacting directly then with that data in the cloud. So these tools are things that to me are kind of in a prototype state and are going to bridge the gap between the current users that use a tool like Earth Explorer or GloVis to where you can use a tool like this and just more easily interact with the data but still visualize it. Okay, so what does STAC do for Landsat? It's obviously not the complete metadata. However, when we reprocess collection 2 in the cloud, we'll be continuing our legacy of our MTL or ODL files. We're going to be adding a complete XML metadata file as well as a complete JSON file. So metadata will be available in multiple formats for Landsat, including the STAC JSON. So it's the big thing with STAC is it's not going to be just another big database. If you currently use our tools like Earth Explorer or GloVis, they're all hitting a relational database. However, this new tool that we're developing isn't. It's all open source. It's using the JSON or the STAC metadata. It's using RioTiler. It's using Lambda. All of it's open source, and it could be extensible to any data set that uses STAC and COG. So that's really important because it not only opens up our data to a tool like that, but it opens it up to a lot of the other tools like the previous session that, who was talking earlier, to tools that anybody might want to develop. So I think it's really important because it really opens up our data set for other developers. So one other thing is we've been talking within USGS about the standards of STAC and COG, for example, and our Data Lake Governance Committee is discussing things like, do we use STAC for all of the USGS data sets that we're going to be putting out? Concepts like the SATA API browser that you're seeing on the right side give us that capability to look at other data sources together with Landsat. In this case, what you're seeing is Sentinel and Landsat together. And USGS is also talking about the concept of Earth Map, which basically brings together multiple types of data that we have within USGS into one conceptual framework. So these are the types of concepts that we're discussing. And I think Landsat's a little maybe out in front with what we're doing, but I do think it's really a path setter. So I do expect to see us move further along this path. And I think that's all I have.
Questions? Does anybody have any questions for Christy while we're waiting for Amy?
Is there any standard on how to associate stack JSON file with your data file? Like in OpenDAP, if you have a data file, you know how to doctor the URL to get the metadata for the file.
So the standard for the STAC metadata is going to be the 0.9 standard. And I think we'll be putting some more information out about what's in that in the near future. Is that what you're asking?
I'm asking, how do I find a stack file given a GeoTIFF file? Like if I know URL for GeoTIFF file, how do I find the stack file?
SATA API browser, I suppose.
Well, it should live along the metadata will live alongside the GeoTIFF, so they'll all be in the same path.
Right.
So,
like the path that you get will be a let's see, within the Amazon infrastructure, if you use our current machine-to-machine API and the structure that you go through to get to an image, it's going to look very similar. The tags we've used are very similar within the cloud. And so I think as we put more information out, you'll see what that looks like. But everything for an image all lives in one basic area in the cloud, including the STAC JSON.
Is there a standard, maybe how to package your data with?
Yeah, there will be some standards in terms of what all those tags look like. And like I said, if you look today at how we store our data on-prem, it's going to look very similar. So you're going to see a Landsat bucket, you're going to see an instrument, you're going to see a path and a row, and then finally the image. I think there's a date in there somewhere. So,
thanks.
Yep.
okay, we're going to move on. Thank you, Christy. All right, Amy is going to be talking about using STAC for small sats for a NASA program. That worked before.
Put it on at the end.
At the end, okay. I even tested it before.
I can bring it on my laptop too. 'Cause I was having some issues. Let me see.
You were?
Oh, I know what it is. Sorry. Oh.
All right. All right, there we go. Cool. I was
All
gonna give you
right.
one more chance, and that was it.
That was my nightmare. So yeah, so basically, I'm talking about an application of STAC that we're using for NASA called NASA's Commercial Satellite Data Application Program, or CSDAP. This is a new program. This is my first time talking about this program, so I'm interested in what you guys, what questions you guys have. And this, this acronym is weeks old, so yeah. So as an introduction, my name is Amy. I'm a data engineer at Development Seed. In addition to this project, we work in a number of different projects using STAC. I want to give a big thanks and shout out to my colleague Anthony Lukash, who did all the work. Anthony is also a data engineer at Development Seed, based in Calgary, which will become important later. So what is CSDAP? So CSDAP stands for the Commercial Small Sat Data Acquisition Program. So it's a NASA program to support the data needs of principal investigators. So principal investigators, apply to NASA for funding to complete some research. They might want to use data outside of the NASA ecosystem. This program basically enables us to acquire enables NASA to acquire commercial satellite data and provide that data, make that data available to its research community. So it's very much in line with the sort of theme of this ESIP 2020, which is all about public-private partnerships to increase resilience and enhance the socioeconomic value of data. So current state of CSDAP, as I mentioned, is a pretty new program. It's actually been around for a while. Just the tools that we're building are pretty new. So in the past, the program has existed for about a year or so, research have been emailing NASA administrators, these data experts, basically making requests for data, and it's been a very sort of manual process through emails and spreadsheets. So what we are working with the NASA team to do is basically create tools and infrastructure to make this a much more automated process for both making requests for the data and delivering that data to the cloud. So in the future, we're going to be onboarding additional providers. So right now, the current providers are Planet, Spire, and Maxar. Those are the current providers as part of the CSDAP program. However, for this first phase of development in this building this automated pipeline, we are providing a search and discovery of planet imagery. So this is basically imagery that we've worked with the NASA team and NASA PIs to define a bunch of planet orders that we want to make and ingest into the NASA CSDAP program. So as of today, we have 14.8 million STAC items. That's representing 64.9 million files in storage and 2.1 petabytes. So just as a point of interest, basically NASA has these agreements with these commercial small sat providers, and one of those agreements is a certain allocation of planet data in square kilometers. And as you can imagine, when it was a manual process, it was quite slow to ingest large volumes of data. So as of about Thanksgiving time, NASA had only ingested about 3%, some very small percentage of that total allocation. So this pipeline that Anthony mostly built, basically over the course of American Thanksgiving, which was of course not his holiday, was able to ingest the remaining 97% or so of the allocation. So a little bit more about what that workflow looks like. So we call the Planet Orders V2 API, specifying an S3 delivery location. That V2 Orders API basically is able to deliver us the data to that sort of callback location after the data has basically been processed to whatever specifications we've given. So, this is delivered to an S3 location, which enables us to kick off an ingestion workflow triggered on the delivery of a manifest file, which is basically a description of the order. That manifest file lands in our S3 location that we've provided, and then that we parse that manifest.json file to get a list of all of the files to be delivered. We pull for all the files, make sure they've all been delivered, or else fail and retry. We parse the metadata JSON, so that's basically information about a particular item to generate our version of a stack item. Download thumbnail to our bucket, update stack item, copy assets to storage folder, update stack item, and then finally submit that stack item to our Stack API. So if you guys are familiar with AWS step functions, basically what that workflow looks like, or visual learner, basically it's a long series of steps, and just also represents how we handle failures by basically all of those steps basically result in an error handling scenario, which enables us to basically reprocess things easily. Okay, so anatomy of a planet delivery. So we have our bucket, we have our inbox, where we're going to watch for new manifest files that will enable us to basically generate those stack items that we were talking about. We have the random GUID representing the planet order ID. We have our order split into numerous parts, and an order can be made up of multiple scenes. So basically, we're going to be receiving as many parts as we have ordered scenes in our original order. Then Planet has this idea of item types. So we're going to have nested structure under that and a Planet item ID. And this also becomes important when we're generating the stack item, which I'll talk about in a little bit. But basically, item IDs are a Planet concept that is not unique. It could also be, it's not unique, and basically the combination of an item ID and an item type is unique. So that's what we use to generate our stack IDs. And then we have a delivery manifest, which basically enables us to check that we got everything that we ordered. So this is an example manifest. You see there's a number of files. One thing you might notice is that the first thing in this manifest, which is on the right-hand side, it's kind of small, but basically the first asset is JSON metadata. So they consider this metadata file about the scene to be itself an asset, which is fine. We do the same thing. So basically, decision points in creating our stack items from Planet metadata. So these are just like the slight bits of interest. Pretty much in generating our stack metadata from the Planet metadata, everything was pretty straightforward. So these are just sort of the minor points that we considered when we were generating our stack items from the Planet metadata. So we maintain that Planet metadata.json file as an asset in our stack item. We create a unique ID using Planet's item and item type, since item IDs are not unique for Planet. And then mostly straightforward is mapping all of the properties from the Planet properties to the Stack EO properties. So probably this is a good thing that it wasn't like more complex to figure out that we should map, EO platform to platform, EO instrument to instrument. The only thing that was slightly concerning was the exception of off-nadir, which I guess Stack expects to be a positive number, whereas Planet was providing both positive and negative numbers. So we did an absolute mapping there. And all the other Planet properties, we don't throw them away. We keep them as sort of an additional property that's prefixed with PL. Discussion topics. So one thing that's come up a little bit earlier as well is, product processing. So both NASA and Planet have the idea of sort of processing levels or processing types. So pen sharpened, analytic, there's a whole bunch of these within the Planet ecosystem, and then NASA has more broadly levels 0 through 4. And it came up in our discussions internally. It might be of interest to people to be able to sort of filter on these types of processes. So is that something that we might want to consider normalizing going forward so that people can actually make those search queries? So current and future work. So we're going to be onboarding new providers, and it's to be seen how easy or complex it is to actually incorporate other providers' metadata, assuming they have an API even for us to generate the metadata, the STAC metadata. How complex that is going to be, it's an unknown at this point. And then we're going to be, these are new features basically that we're working on, enabling users to generate CSVs from data parameters to include cost estimates in their proposals. So the whole idea of the interface that we're building is to enable principal investigators to search the commercial smallsat data programs holdings and include requests for that data in their proposals. So we're basically, the interface that we're working on is enabling principal investigators to both do that search and cost estimate experience. And then we're also working on improving our STAC database query performance. We have a pretty large STAC catalog at this point. So we're just working on making sure that that is performant to make the interface experience enjoyable. So that's all. Thanks.
We've got time for one question. Joe. While you're waiting for that, so actually in regards to the processing level, so there is some discussions going on. I think we've actually talked about that. There's this ARD conference that there's been a couple of, and so I recently actually just saw Ignacio from Planet, and we were talking about sort of the next iteration of that. And so there is some sort of background conversations that we're hoping to sort of group to, get some people together to figure out standardized processing levels for this type of data. So Joe.
Cool. Amy. Thank you. So when you're doing the cost estimates, I guess, are you doing some sort of like join on how much it costs coming from the provider with what is already in the catalog that NASA already owns?
Yeah, so I sort of glossed over this. It's actually, it's not cost because NASA already has agreements with all of these smallsat providers, it's actually just the egress cost. So it's going to be whatever the volume is, how much it is to egress from S3 to whoever they want to deliver it to.
So this is the cost for the researcher to egress the data out of AWS to wherever they want to use the data?
Yeah.
Okay, cool. Yeah. But if they want to use the data where it is?
That should be fine, yeah.
Okay, cool.
It'd be zero.
Thanks.
All right, thank you. So next up, we've got Dan from Element, and he's going to be talking about what we're doing at Element with STAC.
Hello, so I'm Dan Pallone, and I'm going to be talking about kind of how we're using STAC. So with the theme of this ESIP of being kind of the public-private partnership pieces and how to kind of leverage data, we kind of straddle that and we work on both sides of it. And so I wanted to kind of talk through some of the places where we've used it. So I thought it was clever to do a STAC IRL, and then I felt like I had to expand the acronym, and then it got way less clever. So anyway. So I want to start out, Matt talked about this in the beginning, kind of the why STAC. And really, I think this translates into, I think when people ask that, what they're really asking is why not ISO 19115, or why not Echo 10, or FGDC, or Diff 10, or UMM, or CSDGM. And really what it comes down to is, when we pick a metadata standard, there's a technical component to it, absolutely. And there's a lot of argument about, couldn't we do this with other technical, can't we do this with ISO, or can't we do this with Diff? But there's also a business decision piece of it. We have to kind of look at it from that perspective. And so when we've looked at places of what metadata standards do we want to use and why did we end up on STAC, we looked at it from both perspectives. And on the technical side, there's the data use focus. This is a big piece of it for us. So this really looks at, what is the user trying to do with this data and which standard gets us the best access to that. And I'll talk about that some more later. But going at, kind of the examples that Christy gave with getting at Landsat, wanting to be able to interact with that data, what standards get us the best way to be able to do that? It's implementation based. And what that means is that nothing gets added to the STAC spec until there is at least a reference implementation or some kind of implementation. Like as part of those STAC sprints, that standard's evolving, but code is being written and there's actual examples out there and it's ready to be used. The next one, the cloud ready, right? So it's a modern, like when Tom was talking about kind of that evolution that fits in great, like it's that evolution of where we are. STAC was built in this time of looking at, is it network friendly, and assuming kind of on the back end of this, there's a way, like there's links straight through into bands to get to bit level access to this data. It's a core piece of kind of what makes STAC. Static catalog support, the ability to kind of just stand STAC alone, put some files on disk, metadata records on disk, and not have to have infrastructure behind it. And the simplicity, the JSON representation, the ease of use of it. On the business side, the acceptance in open data and the commercial data side of things. So on the open data side, Landsat's a great example of that. We were just talking about Planet a minute ago. Planet uses STAC extensively in data that they push out. On the commercial side, and there's other examples I'll talk about in a bit. Rapid evolution, it moves quickly. STAC is not that old, and each sprint has added new capabilities, new features, which turns into new code, which turns into a usable capability. And then the diversity of the community. So kind of at a high level, looking at the things we've talked, USGS, Christy talked about leveraging it there. AWS uses it for the open data program, a lot of the data in the open data program. NASA, I'll talk about some. Maxar makes their, when they put out like disaster response data, there's a STAC catalog sitting next to it. Australian, Geoscience Australia takes advantage of STAC. SpaceNet is an AI ML kind of open challenge. Data that's available from SpaceNet generally has a STAC catalog sitting next to it. And so it's pervasive in a lot of the circles that we live. So how are we using STAC? I wanted to talk about kind of the different perspectives. We come at it from a couple different perspectives here. So one is from a consumption side. So we have a disaster response tool, we call it FilmDropDR, and the idea of this is to be able to rapidly put together an overlay of visualization in a disaster scenario. So make it immediately available in the cloud and push it all the way out to the edge on like a Snowball Edge device, an AWS Snowball, that we can actually put in situ. Architecturally, at a high level, it kind of looks like this, but the key piece is right here, this group of basically data aggregators. And so what happens is this is all sitting serverless, sitting in AWS. When there is some kind of triggering event, we can kick this off. And these data aggregators all spin up in parallel and begin pulling in data from lots of different sources, relevant sources for the particular disaster that we're trying to do, and make use of STAC metadata sitting next to this data. So again, using Maxar as an example, Maxar puts out freely available disaster response data, and they sit a STAC catalog right next to it. We can hit that and begin pulling that data in and make it available. And so what we end up with is being able to pull in, that's OpenStreetMap underneath. The earlier image was a MODIS image. This is a high resolution Maxar image. This is all over California on the campfire, but all of this can be harvested and pulled together and just immediately made available, and then partitioned out or chipped out, put onto an embeddable device that can be taken in situ with STAC metadata sitting next to it to describe this whole thing. So that all that data is all the relevant metadata that's attached to it goes with it. So that's on the consumption side. On the kind of exposing STAC, so some of the projects we worked on involve getting data out there, and we exploit STAC here too. So this is a link to, or this is a screenshot of what was the CMR STAC API. It was a proxy we had put together coming out of one of the STAC sprints. This has since been adopted by NASA and is formally out there as CMR STAC. And what that does is it takes all of the NASA metadata, all of the holdings in the NASA CMR, Common Metadata Repository, and exposes that through the STAC API and in STAC format. Another one, EarthSearch. This is a deployment sitting on top of AWS's Open Data Program. This leverages SAT API underneath of it, or SAT utils underneath of it. And this basically, any open data that's put out there in AWS's Open Data Program with a STAC catalog next to it, we can index it, surface it, and make it available for searching and accessing in place. And it's just a thin service that exposes all of the STAC metadata that's hosted there. And then kind of in a bigger sense, so not just using it to present data, we provide the back-end processing, so ingest, archive, and processing for Capella Space. They're a search and rescue, they're a SAR, synthetic aperture radar commercial data provider. Ultimately, it'll be a 36 satellite constellation. All of that data comes in. We do everything from the initial ingest all the way through to surfacing to end users with STAC records. It is chased all the way through from one end to the other. It's used for discovery, it's used for process tracking, it's used for inventory management. And so in that case, we're actually producing STAC records and running those all the way through. And then lastly, I want to talk about this one. This is where we're kind of pushing STAC a little bit here. So this is not a formal part of STAC, but it's kind of the next piece that we wanted to integrate, is this idea of exploiting STAC for processing and provenance. And so what we do here is when we have, with the NASA Access proposal, we work with Pangeo Group, NCAR, University of Washington, and NSIDC to look at ISAT-2 data and how can we make, so basically in talking with the University of Washington and some of the scientists there, they wanted access to ISAT-2 in kind of a cloud-friendly format, so similar to what Christy was talking about from Landsat. And so we took a look at ISAT-2 and we put together a processing pipeline, and what we did was we started with STAC from the very beginning. So for every record that we pick up from NSIDC, there is a STAC, or every granule, there is a STAC record attached to it. We've added an extension to that, which is basically, we call it the process field, which describes the processing we want to do to get it from its source format to what we ultimately want to put in an S3 bucket and make it cloud accessible. And so this kind of, it's a lightweight kind of processing stack here, serverless. And if you think of it kind of the Unix model of kind of chaining commands together. So what we can do is we can use a STAC record to define, hey, here's the next processing, or the next processor we want to apply to this record. Goes through. Pick that up, we find the right processor, we process it, and then we actually augment the metadata record to track provenance. So we can tell you everything that happened to this granule from the beginning to the end. When it comes out of the other end, if there's another layer of processing that happens, then there's just another process step that gets added to that record. It goes back through the loop, picks up a different processor, and again, at the end, that metadata record that the user has access to has the full provenance history of everything that happened to that granule from start to finish. We're applying this also, working with Geoscience Australia to reprocess or to repackage is probably a better word, Sentinel-2 data. Currently in JPEG 2000, we're repackaging some Sentinel-2 data over Africa into COGS with STAC records sitting next to it. That's okay. And making that data available as COGS with STAC metadata sitting next to it, and we're using the kind of that same architecture, that same processing pipeline to move that. All right, so it's not all sunshine and roses. I want to be upfront about that. So we talk about challenges using STAC. The static catalogs are fantastic. What it lets us do is, or what it lets anybody do, is drop a static metadata file next to the data, and it's accessible. There's not an infrastructure behind it. There's not, you don't have to disconnect these two things. They're right there. But it does mean that when there are changes, you then have to update those catalog and maintain those catalogs. Part of that could have cascading effects if you have STAC supports linked catalogs and catalogs to collections to items, and you potentially have this cascading effect of how do you do those. And in some cases, the simpler answer is just regenerate the whole thing, which implies that backing it with some kind of a source of truth metadata. And so like in the case of Landsat, you have the MTL file or the ODL sitting behind it, and then STAC is generated off of that. We've done similar things in the past. Versioning is now appearing. 0.9 release candidate's about to come out for that, and that includes versioning support. That'll make this life easier for this and allow users to kind of navigate from older versions and newer versions and know where to go. Metadata mapping itself is pretty easy. It's pretty straightforward to take, an ISO record or a 19115 record, map it into a STAC record, or take an Echo 10 record and map it into a STAC record. But the end user focus of STAC means that different things are prioritized, and different fields may be surfaced or surfaced in a different way. The example Matt gave in the beginning of kind of the common band names is a great example of that. Users want to be able to say, I just want to get at the blue band over this area, or the shortwave infrared band over this area. That's not generally represented that way in a metadata file, in kind of the standard archival metadata records. And so what that pushes us into is potentially having to inject additional metadata or go back to a data provider or finding that from somewhere. So CMR STAC, for example, takes that approach. It has to whitelist the collections that we can produce meaningful records for, and it potentially injects additional information to create a meaningful STAC record on the other side. Some of the key use cases around STAC really rely on the underlying data organization. It's not strictly coupled. You don't have to do that. But the examples that like Christy gave with trying to be interactive with Landsat, when we talk about moving ICESat2 and being able to interact with ICESat2, it really wants to take advantage of net accessible storage. And so that's where you get at things like GDL with HTTPS. So GDL has built-in support. If you can hit a stack record, pull out a URL that points to a cog, GDAL can just hit that and natively pull bits out of that record, and that works great. It doesn't work as well if you're pointing to a compressed zip safe file for Sentinel, where you just can't manipulate it that way in place. And then it also plays a role, the data formats and the implementations play a role in data access. So the examples Matt showed hitting sat fetch and sat search, there's an example he can give hitting the Sentinel Hub version of Sentinel where it's stored as JPEG 2000. The open source driver for JPEG 2000 is implemented in such a way that it's extremely chatty with the backend service. The net effect of that is it's slower than hitting a COG implementation. And also it can get really expensive in like a requester pays model hitting up against a public URL. The GDAL HDF driver is another example. Last I checked, this might be outdated, I hope it's outdated, but the last I looked, GDAL HDF was implemented as actually fetch the HDF file and then subset it locally. And it almost defeats the purpose of what we're trying to do by indexing into that file. And then lastly, rapid evolution absolutely cuts both ways. Things break, that's just the reality of it. Version 8.0, which is out there now, or I'm sorry, version 0.8, which is out there now, reorganized the EO extension and a handful of other things, and really had kind of it was like, okay, this is a big version to get out. It's really important to get that out before some of the Landsat metadata is generated to make sure that we kind of all align, because there can be breaking changes. The versioning that's introduced in 0.9 will help sort a lot of that out, but it's there. And then I mentioned you may need to recreate and reorganize metadata based on changes. All right, so circling it all the way back around, why STAC? For us, STAC is about the user experience. Like that's really what it comes down to. It comes down to, this is a metadata format, and I should have said this in the beginning, I'm a metadata pragmatist. I'm really not a fan of any metadata, but it's like one of those necessary evils. It's really important. And so which one enables the best user experience? And from our perspective, for the use cases that we had, or that we have, STAC is the one that provides that. That end user focus is really key, and it enables the kinds of demos and the kinds of data access patterns that you saw earlier today. So that's it. I think I'm everybody to lunch on time. Thank you.
All right, thank you. Yeah, we have a few minutes. Is there any questions for Dan? Up here in the back, or for any of the speakers, except for Tom. I think Tom ran away.
There we are. Okay, I think this begs the question. A couple of years ago, because we're talking, I like the way that you separated it, practically technical drivers and business drivers. I just wonder, was the foresight there a couple of years ago, 3-4 years ago in NASA to use STAC rather than investing so much effort across the DACs into UMM to make it mandatory for everybody to use UMM, then to reorg stuff at STAC and, to roll out, openness and a couple of business drivers as the justification for why one would then use STAC. And by the way, this is maybe throwing the cat amongst the pigeons. There's business motivations from all around the place to use this and then use that and whatever. And I'm not getting negative on it. I just want, your opinion on that.
Sure. Yeah.
Thank you very much.
Yeah. So I think there's a couple pieces that. So one, I want to be clear, I can't speak for NASA, but it's important to consider the use case though. So UMM had has a set of specific use cases. So one is the list of metadata standards that I had out there. They exist, and there's a ton of data in this community in a bunch of different metadata formats, and that's the reality of it. And then when you incorporate international data, it expands again. And so UMM provided a mechanism to kind of bridge across those things and to try to, I don't want to say harmonize, but gives the CMR the ability to deal with a variety of existing metadata that was there, and there would have to be a major investment and an upheaval because there are people that use this metadata in these formats, right? So the UMM provided that kind of cross mapping that was critical to do it. The other thing that is important is that it is a different use case. UMM and a lot of the other metadata formats go at an archival use case, right? As a data provider, and NASA has a charter to be, you know, a data steward and to maintain and archive this data. That is not the goal that STAC is going after. There are absolutely pieces and fields and relevant capabilities in ISO and everything else that STAC, just as a user-facing search, discovery, access kind of a metadata format, just doesn't necessarily need, but that has to exist. And so I don't know if that's exactly an answer to your question, but I think UMM does have two very specific use cases, neither of which that STAC really intends to go after. And in fact, the STAC CMR implementation, it was discussed, and an approach is actually using the CMR's UMM capability to then map into STAC, and it provides that integrity that we know we can map into STAC from anywhere. Yeah.
Okay, do we have any more questions? No, okay. All right, well, thank you to all the speakers, and thank you all for coming. If anybody has any input on the takeaways from this, I guess I'm supposed to fill this out. Do I have any volunteers? I guess I was supposed to do this before, but.
Everybody should use that.
All right, that's not bad.